what we're going to cover in this lecture today is the use of this method called sublist, but we're also going to do a lot of recursion, which you should have done a little bit in CISC121. So when you take your data structures course and your algorithms course, you're going to have to be comfortable with using recursion, because a lot of the fundamental algorithms that we use in data structures are most easily described recursively, and a lot of the fundamental approaches that you take in your algorithms course will also use recursion. In both of those courses, you might see how to take a recursive problem and turn it into a iterative one. We're not going to do that today, though. So I'm going to start with this game called Jump It. It's not the most exciting game in the world, but it is a really nice example of solving a problem using recursion. So you have this board, so it's a linear board. I can represent it as a list or an array. Right? So I have n squares on the board, where n is greater than or equal to 2. You always start at the leftmost square. Right? So I'm always starting, in this case, at the 0. Now that doesn't have to be a 0, but for our purposes, it's 0 right now. And the goal is to reach the final square on the board, right? So the rightmost square on the board. You're allowed to move along the board by taking 1 or 2 steps every time to the right. So you can only move right. You're allowed to take 1 or 2 steps. Every time you take a step, you land on another square. So if I start at the 0 and I take 2 steps, I land on the 80. Right? So when you land on a square, the cost of landing on that square is the value stored in the list or array. Right? So if I were to go from the 0 to the 80, I would incur a cost of 80. Right? And then if I were to go to the 80 to the 6, I'd incur a cost of 86. And then if I were to go to the 6 to the 10, I'd have a total cost of 96. Right? Which obviously is not the lowest cost solution on this particular board. Right? Okay, so for this example, the solution is the following. Right? So I move 1 square to the right, to the 3, then I move to the 6, right? And then I move to the 10. Right? And that's a total cost of 19. Right? So that's pretty straightforward. So if you just looked at that board, I think you would see the solution pretty quickly. The problem now becomes, so what happens, so how do you actually code up this solution? Right? And so because you're working on a list, probably your first intuition is to say, well, I'm going to try to write some sort of iterative solution to this problem. Right? So I'm going to write some kind of loop to solve this problem. But if you try to do that, it's not at all obvious what this loop looks like. Right? To arrive at this particular solution, you might also conclude, well, the way I got the solution is I always took the step with the lowest cost. Right? So starting at the 0, I have a choice between 3 and 80, so yeah, I'm going to choose 3. Right? Now I've got a choice between 80 and 6, so I'm going to choose 6. Right? And now I have a choice between 57 and 10, so I'm going to choose 10, because 10 is the lowest cost. Right? So you might say, well, this works in general. Right? So why don't we just do this in general? And the answer is because it doesn't work in general. Right? Because it might be better to move to a square with a higher cost, because you would have ended up on that square anyway. Right? So so I've got a bunch of squares to the right here, to the left here, sorry. I'm on the 17. And so the lowest cost solution, you might say, well, I should go to the 1, because that's cheaper than 5. Now I've got a choice between 5 and 6, so I'm going to go to the 5. And then I'm going to go to the 1. Right? So your total cost here is 24. Right? But in fact, it's not the lowest cost solution. Right? The optimal strategy is, in fact, to jump over the 1. So in fact, it's to take the higher cost step. Right? Because in jumping over that 1, I end up at the 5, which I need to be at anyway. Right? So it's possible that, it's not just possible, it's often the case where taking the lowest cost step next does not lead to the optimal solution. Right? And now you can see why this is problematic when you try to write a loop. Right? Because there's a decision process that you have to make, and a decision that you make at one point in time, you might have to reverse that later on in order to end up with the true lowest cost. All right, so how do you solve this problem? So the answer is, well, you should try to sketch out some small examples of the problem. Right? So this is how do you solve the problem recursively. And so whenever you try to solve a recursive problem, it always helps to start with small versions of the problem and then work your way up. Right? So if you start with small examples of the problems, it helps you find the base cases. Right? So remember what a base case is in a recursive solution, right? The base case is where you know what the answer is, right? And furthermore, it might help you find the recursive cases, right? So every recursive solution has two steps, right? Or two main parts, right? There are the base cases where you know what the answer is, right? And then there's the recursive part where you reuse your solution to solve a smaller version of the problem, right? So let's sketch out some small versions of the problem, right? So you know that this board size can be 2 or bigger. So if you start out with this board of size 2, right, your solution is obvious, right? You have no choice. You have to take that step, right? So if your board size is 2, there's no choice to move. You must move 1 square, right? Your cost is just equal to the cost of the square that you're on, right, plus the cost of the square that you're going to, right? And remember, we're just going to store these in a list. Now, if your board size is 3, right, you should always avoid stepping on the middle square, right, because there's no point. You're just going to incur a higher cost because you're going to end up, because you can jump straight to the solution anyway. So if your board size is 3, you just move 2 squares, right? And now your cost is whatever the cost is of your current square plus the cost of the final square, right? And if you go up to a board size of 4, which we had back here, this is 5. But if you go to a board size of 4, you can come up with a problem where the optimal choice, where you don't know what the optimal choice is immediately. It's one of 2, but you don't know which one it is, right? You have to evaluate them both. Okay, so if I'm going to write a recursive solution to this problem, I can write it as, I can start to write it as follows. So I'm going to create a method called cost. Right, that's the cost of solving a board. There's my board, right? So the board I'm just representing as a list. I'm going to return the total cost of solving that board, right? So it's a method. The method cost returns the cost of solving the given board, right? I've got 2 base cases, so I stick those at the top of my method, right? At the beginning of the method, right? So the board size is 2. Right? The cost of solving that board is just the sum of the 2 squares of the board. Right? If the board size is 3, then the optimal cost of solving the board is just the current square that you're on plus the final square of the board. Right? Okay, now what are your recursive cases? Right? So your recursive cases are, well, so how do you solve this problem in general? So you know that no matter what square you're on, you can either take 1 step or 2 steps, right? So what I can do is I can take 1 step, right? Because I just look at the next, I can just look at the next square on the board, right? And then I need to calculate the cost of solving the rest of the board, right? Alternatively, I can take 2 steps, right? I can jump over 2 squares. I can just look ahead in the list to look ahead 2 spots from the current position, right? And then I need to calculate the total cost of solving the rest of the board, right? If I can evaluate those 2 costs, then the optimal cost must be the smaller of those 2, right? So in other words, solve for the cost after taking 1 step, right? Solve for the cost after taking 2 steps, right? Whichever one is smaller, that's the optimal cost. Right? So you say, well, how do I solve for the cost of taking 1 or 2 steps? The answer is, that's what your method does, right? Your recursive method solves for the cost of solving that board, right? Finds the cost of solving that board. Okay, so believe it or not, this is the complete solution, right? So here are my 2 base cases, right? Now, if neither of those base cases are true, I reach this point in the algorithm, right? And so what I need to get is, I'm going to take, so after 1 step, that's the board after taking 1 more step, right? Now how do I get the board after taking 1 more step? Well, I've got this handy method called sublist, right? Remember what sublist does? Sublist gives me the part of the list starting at index 1 right? Going up to and not including, starting at index 1, going to the end of the list, right? So in other words, I can compute the board minus the first square, right? After 2 steps, that's the board after taking 2 steps, right? So what do I want to do? Well, I want to compute the list or the board, removing the first 2 squares off the board, right? So that's just the sublist starting at index 2, right? So that's the list after taking 1 step. That's the list after taking 2 steps, right? What's the current cost? Well, the current cost is the cost of the square that I'm currently on, right? So that's just stored in the board at index 0, right? And now I need to know what is the smaller cost, right? So I need to know the cost of solving after 1 step. I need the cost of solving after 2 steps, right? So what's the cost of after solving 1 step? What's the cost of solving after 1 step, right? Well, it's just the cost of solving that board, right? So in your recursive method, right, remember how you write a recursive method, right? You always reuse the method to solve a smaller version of the problem, right? What's the smaller version of the problem every time in this problem? Well, you take a step and then you solve for the rest of the board, right? Or you take 2 steps and you solve for the rest of the board, right? So when you're writing a recursive method, right? So the key in writing these recursive methods is to, first of all, clearly define what the recursive method is supposed to do, right? Don't worry about its implementation, right? So what is cost list supposed to do? It's supposed to evaluate the lowest cost solution to that board, right? And return that value as an int, right? When you write your recursive method, you just assume this is what you assume that your method is going to do exactly what it says it does, right? Now you use the method in the recursive part of the method, right? Even though it hasn't been completely written yet, right? The method's not done until you write this line, right? So I'm just going to assume that cost actually does what it says it does, so I can use cost to evaluate the cost of the board after stepping 1 square. Similarly, I can use cost to evaluate the cost of stepping 2 squares. And then I can take their minimum using math.min, right? And your total cost is just the cost of the square that you're on plus the smaller of those 2 costs, right? And believe it or not, this actually does solve the problem, right? It will, in fact, return the smallest cost solution for any given board. All right. Anybody have any questions about that particular algorithm? I don't know how much recursion they hit you with in CISC121. So this is either very easy or this just went right over your heads and you'll never be able to do this sort of thing in your life. That's not true. But I'm not sure I don't know how much recursion you guys did. Any questions? You want me to go over it again? Okay. I don't think, let me just see if I explain. Okay. Hang on just a second here. I just want to skip ahead to see if I actually talk about what's going on. I don't think I do, actually. All right. Oops, sorry. Now, that's not where I want to be. One of the confusing things when you write a recursive method is that it's often the case that we don't actually tell you how recursion works. Okay, so one of the things you have to remember when you write a recursive method in either Java or Python or C, right? So every time you write a method, right, or every time you call a method, right, you get a brand new version of the method running in memory. Okay? So every time you run a method, you get a brand new version of the method running in memory, right? So a lot of students think there's only one version of the method that runs, right? And if you think that there's only one version of the method that runs, it becomes very confusing, right? Because you think, well, this method modifying itself and this doesn't make any sense. That's not what happens. You get a brand new version of the method every time, right? So the first time I call this method cost, right, you can imagine that there's a version of the method that runs, right? So I'm just going to draw a little box here. So here's my cost method, right? So when this method runs, it gets its own version of the board, right? So it's got a variable called board in it, which is some list, right? And it chugs along and it does something, right? If this method calls itself, right, then what happens is a second version of the method appears. And it also has its own version of the board. Right? Now notice this board is different than that board because when it calls itself, it passes in a different board. Right? So now this cost method operates on its own board. Right? And you know that this version of the method is actually going to call itself twice, but anyway, that's fine. Right? If this one calls itself recursively, right, you get another version of the method. So there's cost. Right? You get your own board. Right? And it does whatever it needs to do. When this method finishes, right? So if this method, in other words, if this method hits a base case, it goes away. Right? And it returns a value back to the method that called it. Right? And so now this method uses the value that was returned by the recursive call, does something with it, and then it finishes. When that one finishes, it goes away. Right? Returns its value back to the method that called it, and then this one uses the return value for whatever it needs to do. Right? So a recursive method calls itself, but you get a new version of the method every time. Right? It's not just one version of the method that runs. Okay, so there's lots of variations of this problem that you could try to solve. Right? So for example, you can take that method I just wrote, and you can modify it so that it also returns a list of moves. Right? So instead of returning the cost, right, can you have the method produce the list of moves that it needs to make to solve the board? Right? So in your copious free time, right, you might consider trying to solve that version of the problem. Right? Now notice here, I'm suggesting you use this version, so I'm suggesting you don't try to return the list. Right? Instead, you should return the cost, and you should store the list here. Right? So assume that someone passes you an empty list of moves, and your method fills in the list of moves with the moves that it makes to solve the board. Right? Okay, now that particular version of the problem, which no one had any questions on, remember that, right? So it has a couple of nice properties. Right? So number one, the rules of the game make it impossible to move to the same square twice. Right? You're always moving to the right. So that's nice. Why is that nice? Because you know the board is getting smaller at every step. Right? And that's one of the key things that you need to have to write a recursive method. Right? You can only write a recursive method if it solves a smaller version of the problem itself at every step. Right? If at any point it tries to solve a bigger version of the problem or a same size version of the problem, you cannot be guaranteed that the recursive method will end. Right? So in recursion, you're always trying to solve a smaller version of the problem. The other nice thing about this problem is that you don't have to worry about falling off the board. Right? It's impossible to make a move that goes off the board. So I don't have to worry about checking indexes or anything like that. Right? Now I can get rid of both of those by changing the problem slightly. Okay, so now we have a board, also a list of integer. You want to start at the left-hand side of the board, right? And you want to reach the right-hand side of the board. The right-hand side of the board, the last element always has a 0 in it. So starting here, you want to get to here. Oh wait, sorry, hang on, sorry. I'm in the wrong. I want to, what do I want to do? This? Does that work? Okay, so starting here, I want to reach that square. That number in the square now tells you how many squares you're allowed to move left or right. Right? So starting at the 2, I'm allowed to move 2 squares to the left if there's a board to the left. Right? Or I can move 2 squares to the right. So in other words, starting at the 2, I have to move to the 4. Right? Now that I'm at the 4, I can move 4 squares left or 4 squares right. Right? I can't move left because I'll fall off the board, so I have to go right. So 1, 2, 3, 4. So now I'm at the 1. Right? Now at the 1, you can go 1 square left or right. Right? And now you have a decision. Right? Should I go to the 6 or should I go to the 2? Right? And it's not at all clear what you should do at this point. Right? So how are you going to solve this problem? Right? Again, if you try to write a loop to do this, you'll probably run into a problem. Right? So let's look at a solution first. All right, so I can move left or right, but if I move left, I fall off the board, so I have to go right. So that takes me to the 4. At the 4, I can go left or right, but I have to go right because otherwise I fall off the board. So I'm at the 1. Okay, now at the 1, apparently I can move right to the 6. So let's do that. And then from the 6, I can't go right, so I have to go left. 6 squares, right? So that takes me to the 3. At the 3, I can't go left because I fall off the board, so I have to go right. And now that I'm at the 5, I can jump to the 0, and there we have a solution. Right? But there's more than one solution to this board. Right? So again, starting at the 2, I go to the 4, then to the 1. Now instead of going to the 6, I can go to the 2. Right? From that 2, I can go to the 2. Now this is interesting when you get to this 2. Right? When I land on this 2, I can go back to this 2. Right? I'm allowed to go 2 squares to the right. So I can technically go back to this 2. But this doesn't help me find a solution because it's just going to spin me in circles. Right? I'm already here. I don't want to go back to this square. Right? So in this case, you move, 2, then 2 to the left, and then 3 to the right, and now 5 to the right. Right? And so in this particular problem, it's often the case that there's more than one solution. Right? And it's often the case that you can find cycles where a move takes you back to a square that you've already been on. Right? And obviously, if you do this, you can end up stuck in an infinite cycle. Right? It's possible to just keep on going back from 2 to 2. Okay, now given the fact that a board can contain cycles, it's easy to make boards where no solution exists. Right? So here I've got a board, 2, 5, 2, 0, and the only possible set of moves is from the 2 to the 2. Right? And there's no solution on this case. Right? So now you have a problem where there's no solution as well. Right? So when you try to solve this problem, you either solve it or you realize that there's no solution. Okay, on that board there, no matter what you do, you eventually end up on the 1. Right? So no matter what sequence of moves you make, you eventually end up on that 1. As soon as you end up in that 1, you end up in a cycle. Right? And you don't need cycles to produce a board that has no solution. Right? So here's the board, 1, so I have to go to the 100. Once I step on the 100, there's no further legal move to make. Right? And therefore this board's not solvable either. Okay, now unlike the jump it problem, it doesn't look like this board gets smaller in any obvious way after each move. Right? So again, in the jump it problem, the board always gets smaller. Therefore, it's easy. Well, you can conclude that there's probably a recursive solution. Right? In this one, it doesn't look like the board gets smaller, but in fact, it does. Right? So in fact, there is a way to write this so that the board does in fact get smaller. So how does the board get smaller? Well, you never want to step on a square that you've been on before. Right? So every time you step on a square, you want to rule out that square as part of a further solution. Right? So ruling out that square as part of a further solution means that the size of the board decreases by 1. Right? So in fact, the board does get smaller. Now, I need some way to indicate that I've actually been on a square before. So we need some way to do that. All right, so let's write a recursive solution to this problem. So our recursive cases are, right? So remember, so the question here is, the problem that we're trying to solve is there a solution to this board? Yes or no, right? So our recursive cases are, you're on some square somewhere, right? You can look at the value of the square, right? So you look at the value and you ask yourself, can you go left without falling off the board, right? If the answer is yes, you reuse your method to solve the problem. Can I solve the board by moving left? Right? Then you ask the question, can you move right without falling off the board? If the answer is yes, you use the recursive method to solve the problem. Can the board be solved if I move to the right? Okay, so I'm going to write this method called isSolvable. Right? Your board is just a list of values. Now the index, that's the square, or that's the index of the, that's the square that you're currently on, right? So if your index is 0, you're currently at the left-hand side of the board, right? If your index is 1, you're currently on the second square of the board, and so on and so on. The method is going to return true if that board is solvable starting from that index, right? It will return false otherwise, right? Now, again, when you write a recursive method, right, if you define exactly what it is the method is going to do, right, before you start writing the method, right, you can use that definition, right, to help write the recursive method. Right? Oh, notice here the method does not modify the board, right? Which is a nice, so methods that, when you have a method like isSolvable, or some method that takes in a list, right, because you have a reference to a list, that method can change the contents of the list, right? So it can remove elements from the list, it can add elements to the list, it can set elements of the list, right? Most of the time when you write a method, you want to avoid changing the state of the list, unless that's exactly what the method is supposed to do, right? So obviously a method that sorts a list should change the order of the elements of the list, right? But otherwise, right, if the method is trying to solve some problem like, is this board solvable, right, it's generally better if you don't modify the state of the list. Right? So here, this method promises it's not going to modify the state of that list, or it's not going to permanently modify the state of that list. Okay, so we've got our base cases, or we've got what look like to be our base cases. So we can just scribble those down. Right? So the first thing I'm going to do, I'm going to get the value of the square that I'm currently standing on, right? Because that's the thing that determines, that's the number that tells me how many squares left or right I can go. Right? Now, I need some way to indicate that I've been on this square already, right? So the way I'm going to do that is I'm going to change, right, the square that I'm on. So I'm going to temporarily set it to -1. Right? Now notice back here, the method promises not to permanently modify the state of the board. So we're not. I'm going to temporarily modify it. I'm going to change it back later on. Right? So I'm going to replace that -1 back with the original value later on. Right? So as far as the caller is concerned, they never see a modified board. Okay, now, can I go left? Right? So when left is true if you can solve the board by moving left. Right? So I'm going to set it to false. Right? I'm now going to ask the question, can I actually move to the left? Right? So how do you know if you can move to the left? That's the square you're currently on. Right? That's the number of squares you have to move. Right? Moving to the left is equal to computing the index minus the value, right? Because that's going to be the index of the square that I land on. Right? Is that a valid index? Well, it's a valid index if that's greater than or equal to 0. Right? So if that's true, then I can in fact go left. Right? So I just call isSolvable. These are not the base cases. The base cases are going to come later. This is the recursive case, sorry. So can I win left? Or can I win by going to the left? Well, maybe. How do I know? I just use isSolvable to answer that question. Right? So is the board solvable if I start at that index now? Right? So in other words, if I start at the current square, moving to the left by value squares, right, is the board solvable? Okay, now what about going to the right? Right? So going to the right is identical to moving value squares to the right. Right? What's the index of that square? It's index plus value. Right? Is that a valid index? Well, it is if it's less than the size of the board. Right? So if that's all true, then I can call isSolvable moving to the right. Right? So isSolvable, moving to the right, this board. Right? And now if either of those are true, oh yes, right. Right? So if win left is true or win right is true, right, then you know that the board is solvable. If they're both false, then you know that the board is not solvable. Okay. Now remember back here, I modify here. back here, I modified the board, right? I changed the value of the square that I'm currently on to indicate that I'm on this square. So I have to undo that change before I return from the method, right? In order to satisfy the promise that the method does not change the state of the board, the state of the list, right? So unset the value at the index and then return your value. Right? So that's the recursive part of this method. Now, what do the base cases look like? Okay, so remember the base cases occur when you know the answer to the problem, right? So base case occurs when you know the answer to the problem. So one way that you know the answer to the problem is you land on a square whose value is -1, right? Because if you land on a square whose value is -1, you've been on that square before. So the current solution is not, so the current, making that move does not lead to a solution. Right? So in other words, you can return false if you land on a square that you've been on before. Right? Now, when else do you know that the problem is solvable? Well, you've landed on the last square. Right? So if you land on the last square, then you've solved the board. So in that case, you can return true. Right? So your base cases are trivial to write in this case. Right? So if the square that you land on, if its value is less than 0, or if it's equal to -1, right? That's not a solution, so you return false. Right? Otherwise, if that index is equal to the size of the board -1, you know you're on the last square, you return true. Right? So you take these base cases, stick them in here, and that's your method that solves this problem. That's your recursive method that solves this problem. All right, any questions on that particular algorithm? All right. Okay, so now suppose I give you a list and I want you to move the smallest element in that list to the front of the list. Right? So if I asked you this problem, then the obvious way to do this is you would find the smallest element in the list. Right? So you'd write a loop, find the index of the smallest element, right, and then swap that index with the front element. Right? Now, what happens if I ask you to do it recursively instead? Right? So how do you move the smallest element in the list recursively so that it ends up at the front of the list? Right? Okay, so suppose this is my original list at the top here, right? So 8, 7, 6, 4, 5, blah, 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 right? The smallest element is obviously the 0. I need to move that 0 to the front of this list, right? So I'm asking you for a recursive solution, right? And so now you ask yourself, well, how do I write this recursively, right? So answer, I have to, if I'm going to write a recursive method, then I want to solve a smaller version of the method at every step, right? So what happens if I ignore the first element, right? And instead, I move the smallest element in the rest of the list to the front of that sublist. Right? So in other words, suppose I move the smallest element in that blue list to the front of the blue list. Right? Never mind how you do it, just assume that you can do it. Right? So if I can do that, then I know that my overall list looks something like that. Right? That's the element at the front of the list. That's the element that's smallest in the rest of the list. Right? How do I move that 0 to the front? Well, I just compare these two values, right? If the second value is smaller than the first, then I just swap them. Otherwise, I don't do anything and I'm done, right? So in other words, if the second value is not smaller than the first one, then that first element was the smallest element in the list all the time, right? Right. So once again, right, ignore the first element, move the smallest element in the sublist to the front, then compare the two elements, the first two elements of the list, right? That problem right there, right, move the smallest element of the sublist to the front of the list, or to the front of the sublist, is a smaller version of the original problem, right? The original problem is move the smallest element in the entire list to the front of the list, right? Now you've got a list that's one smaller, right? So you can use recursion to solve this problem. Right? So this is min to front solved recursively. Right? Ignore the base cases first. Right? So step 1, move the smallest element in the sublist, not including the first element, to the front of the sublist. Right? So the signature of my method is min to front sum list. Right? I want to move the smallest element in the sublist, not including the first element. So I just get the sublist, not including the first element, right? And pass that to min to front, right? Min to front does some magic, right? Moves the smallest element in the sublist to the front of that list, right? Right? So in other words, that entire step, you just replace with one call to the recursive method, right? And now you do the comparison, right? So I get the first element in the list, I get the second element in the list, right? Now remember, sublist doesn't return a new list, right, for Java lists, right? Sublist returns the part of the list that contains the sublist. So if I modify the sublist, the original list is also modified, right? So in other words, if I move the smallest element in the sublist, so if I move the 0 to the front of that sublist, right, then in the original list, that 0 really is at the front of the sublist, right? So I get the first and second elements. That's just t get 0 and t get 1. And now compare them. Right? If second is less than the first, just swap second and first. Right? And away you go. Right? So there's the recursive part of your method. Now how do you know that you're done? Right? So remember, you know that you're done when you reach a case where you know what the answer is. Right? So when do I know that the smallest element really is at the front of a list? Right? Well, if the list has no elements, or if the list has one element, you're done. Right? If the list only has one element, then the smallest element must be at the front of the list. Right? If the list has no elements in it, then there is no smallest element, so there's nothing to do as well. Right? So if the size of the list is less than 2, you're done. You just return. Right? And believe it or not, this does in fact move the smallest element to the front of the list. Okay. Any questions on that method there? All right. Now, suppose you've got this min to front method, right? So I've applied min to front to the whole list, right? So the 0's now at the front, the 8's now in the second spot, right? What happens if I call min to front on the sublist? Right? So in other words, what happens if I call min to front on the rest of the list? Well, that's going to move the 1 to the front of the sublist, right? And now notice that the second smallest element is in the second location in the list. If you do it again, right, call min to front on that sublist, right, well, the 2 is going to move to the front, right, and now the third smallest element in the list is in the third location in the list, right, and if you keep on going, right, you will eventually sort the list, right. That's the selection sort algorithm, which I don't know if they taught you in 121 or not, right. Selection sort, you repeatedly move the smallest element in the sublist to the front of the list. Right? They probably, if they showed it to you, they would have shown you an iterative version of the method, right? But you can write it recursively as well, right? I've got min to front, right? So how do I write selection sort recursively? Well, I just move the smallest element to the front of the list, and then I sort the rest of the list, right? When do you know that you're done? If the list has one element in it or 0. So if the list has one element or 0, you're done, you do nothing, right? If the list has more than one element, then you just recursively sort the list using selection sort, right? And that's the recursive version of selection sort, right? Which, if you can get past the recursion, is probably easier than trying to write the iterative version of the method. Do we want to do this? Okay. So there's only 2 steps in that selection sort algorithm, right? Step 1, you move the smallest element in the list to the front of the list, right? Now, how do you move the smallest element to the front of the list? So it turns out that has complexity big O of n, right? Find the smallest element, so I have to search n elements. Move it to the front of the list, that's constant time, right? So that's complexity big O n. Okay, now recursively, selection sort is going to sort the sublist, right? So that's only step 1, right? So that moves the smallest element to the front, and now I'm going to recurse. Right? So now I'm going to call selection sort again, this time on a smaller list, right? This time on a list of size n minus 1. Right? So if you scribble out the recurrence relation for this, which they also should have told you about in CISC121, right? So if Tn is the number of operations needed to selection sort a list of size n, right? Then the total number of operations is equal to the number of operations needed to sort a list of size n minus 1, right? Plus big O of n, right? Move the smallest element to the front of the list. If you solve that recurrence relation, you end up with big O n squared, which is in fact the worst case time complexity of the selection sort algorithm. Right? Did you look at complexity of recursive algorithms in 121? All right, good. So that should be all, well, that part here then should be a review, right? I don't know if the rest of it was a review to you or not. All right, any questions on today's lecture? Super. So if I throw this on the midterm, you'll be able to do it, right? Yes? Okay? All right. That's it for today. We'll see you on Wednesday. You won't see it on the midterm. Don't worry about it.